Welcome to The Explainer. Ever wonder what really happens in that split second after you click a link? Well, today we're going to peel back the layers of the internet, starting with the absolute smallest piece of the puzzle. Let's jump in.
Okay, so let's start at the very beginning, the ground floor of all digital information. I'm talking about the bit. It's the tiniest piece of data you can have. Just think of it as a single yes or no, an on or an off. That's it. One simple choice.
But, one bit by itself can't say a whole lot, right? To build a real language, we need an alphabet. And in the world of computers, that means we've got to start grouping those bits together into bytes.
So, at its absolute core, a bit is basically a light switch. It can be on, which we represent with a 1, or it can be off, which we call a 0. Simple as that. Every single photo you take, every song you stream, every website you visit, when you get right down to it, it's all just a gigantic collection of these tiny on-off switches. Now, here is where things start to get really cool. You take 8 of those little bits, you string them together, and poof, you've got a byte. Just one byte gives you 256 different possible combinations. That's enough for every letter, number, and symbol on your keyboard. It's the fundamental building block computers use for pretty much everything, including the addresses that tell your data where to go.
So how in the world do you turn a string of ones and zeros into a number that we can actually understand? Well, it's all about position. Each spot in that 8-bit byte stands for a power of 2. You start with 1 on the far right, and then it just doubles as you go left. All you have to do is add up the values wherever you see a 1. That's the secret sauce.
Let's take the number 25, for example. We just need to flip on the switches for the number 16, the number 8, and the number 1. See? We put a 1 in those spots, a 0 everywhere else, and that's it. Every single number has its own unique binary fingerprint.
Okay, so you can probably imagine writing out these super long strings of ones and zeros gets old fast. To make life easier, we use something called hexadecimal. It's a base 16 system that uses the numbers 0 through 9 and then the letters A through F. And the really neat trick is that a single hex character can represent a chunk of 4 bits, which makes these long binary numbers way easier to handle.
And yeah, you can see why. I mean, can you imagine trying to read a full 32-bit IP address in pure binary? It'd just be a sea of ones and zeros. It would be a total nightmare. So systems like Hex really save the day.
All right, so now we've got the language down. Let's meet the actual hardware that's doing all the talking, the physical gear that makes up the internet.
At the very highest level, the internet is basically just a conversation between two main players, clients and servers. Your computer, your phone, your smart fridge, those are all clients. They're the ones asking for information. And the powerful computers they're talking to, those are the servers, the ones holding all the websites and the data.
It's almost exactly like ordering at a restaurant. You, the client, make a request. Hey, I'd like to see this specific web page. That request travels across the internet to the right server, and the server, which is kind of like the kitchen, finds what you asked for and serves it right back to you.
But here's the thing. Your request doesn't just magically teleport from your computer to the server. No, it has to pass through a whole bunch of different devices along the way. These are the intermediaries that act like traffic cops, making sure your message gets exactly where it needs to go.
The two most important of these traffic cops are switches and routers. Think of a switch as the mailroom clerk for a single office building. It works inside your local network, your home or your office, making sure an email from your computer gets to the person in the next cubicle. A router, on the other hand, is like the city's central post office. Its job is to connect different networks together, taking your request and sending it out onto the wider internet.
And the way we arrange all of these switches and routers is what creates different types of networks, all based on how big of an area they cover.
And this slide shows that difference perfectly. Over on the left, you've got a local area network, a LAN. That's a self-contained little network like what you have in your house. Then, on the right, you see what happens when you connect multiple LANs together over a long distance. That creates a wide area network, or a WAN. And connecting these individual LANs is really the secret to the entire internet. But it's also where things get a lot more complicated, involving a whole universe of rules and routing to manage all that traffic zipping between networks.
So if we break it down, the main differences are pretty clear, right? LANs are small, they're super fast, and they're usually managed by just one person or organization. WANs, on the other hand, they cover huge areas. They're run by lots of different service providers, and the connections between the LANs are usually a bit slower than the connections inside them.
So, we've seen all the individual pieces.
what happens when you put it all together? What does it look like when you zoom way, way out and see millions of these networks all connected on a global scale?
Well, you get a structure that looks a little something like this. You have your central office LAN, you've got a smaller branch office LAN, and maybe even a single home office LAN. They're all their own little networks, but they're all connected together through that cloud of the wide area network.
And when you take all of those pieces, every home network, every office, every giant data center, and you link them all up with WANs, you get this. This unbelievably complex, beautiful, global collection of interconnected networks. This is the Internet. It's not one single thing. It's a network of networks.
Now, for a massive global system like this to actually work without constantly breaking, it's built on 4 key ideas or pillars. First, there's fault tolerance. If one cable gets cut, your data just finds another way around. Second, scalability. It's designed to just keep growing and growing without collapsing. Third is quality of service. This is what makes sure your important video call stays smooth even while you're downloading a huge file in the background. And finally, of course, security, to protect all of our information as it flies across the globe.
This incredible architecture makes our entire modern world possible. It's built on a foundation of trust and rules designed for openness and reliability. But that brings us to a final and really crucial question. As we connect more and more of our lives to this amazing global network, are we really doing enough to protect that foundation? It's definitely something for all of us to think about.